Let's talk about the randomness associated with the simulation model. Okay, randomness. Um, Usually data and parameters are not deterministic, especially when you develop the simulation model. And then you are using simulation model because of the randomness associated with your data, right? Or parameters. For examples, interval time and service time following the certain distribution or statistical distribution, and choice of customer can follow the probability value, right? And there also sometimes system has a barking behavior or mechanic breakdown frequency, which also following the certain statistical distribution, and then and other actually characteristics associated with the subject system uh, are not really deterministic, okay, right? Like, for example, employee can take a break, right, due to his health or her health issue, right, and so on. So in reality, most of data are not deterministic, as you know. So anyway, in order to represent randomness, we need to use a random variable, right, having statistical distribution. And basically, when we develop the statistical distribution for the random variable, we need observations, right? We need to observe the situation, right? And then based on the observation, we can actually understand this distribution associated a certain random variable, right? So when you drive a statistical distribution, and it can be triangular distribution, and it can be also uniform distribution and exponential distribution. And triangular distribution usually have three parameters. And so triangular distribution has three parameters, and the shape itself is like a triangle. And that's why we are calling this distribution as a triangular distribution. So it has minimum value and the maximum parameter and then mode, right? Also, it has a uniform. Also, you can also have a uniform distribution, which has same probability value over different x values. So in this example, we have x ranges between 0 and 4. So as you can see over the x, it has the same distribution. And also, random variable can follow the exponential distribution with this shape, okay? So its probability is very high when x value is very small. And then this is significantly reduced as x value increases, right? And usually interlevel time of the parallel following the exponential distribution when parallel process following the Poisson distribution. All right. So anyway, once you have statistical distribution, you need to get the random value, right? So simulation generate random numbers for you, so that you can easily use random values, okay, given by the statistical distribution. So today, actually, I will teach you how to generate a random number in simulation, theoretically. So, and then also it is used by the many simulation software. So you don't need to worry about it after this class, and then basically you are ready to generate a random number by yourself, which means you are ready to develop your own simulation software in future if you want it. All right, so representation of randomness. You may wonder, from the given statistical distribution, how we can get the different parameter or variate at each time. Yes, we can get the sample from statistical distribution. That's what you call the sampling, right? So in order to get the sample, you need to have a random number, as I mentioned earlier. So we want to have any number following, let's say we have any number following this uniform distribution. Okay. So that's a definition actually of the random number. So any number following this uniform distribution, and then there is the random variate, or known as an observation. So we want to have any number following a certain statistical distribution. It can be triangular distribution, uniform distribution, exponential distribution, and then discrete empirical distribution. To generate the random variate, a general random number is the first step. Why? Because we need to get the random sample, okay, random sample from CDF of the statistical distribution such as triangular distribution, uniform distribution, and so on. So you need to do the random sampling. In order to do the random sampling, you need to have random number, all right? So that's why you need to generate random number. And don't worry, I will explain the procedure with the example later. So we are using inverse transformation method to get the random number, okay? In other words, to get the random variate, yes, random variate. So first, you can get a sample, okay, get a sample from uniform distribution, okay. So initially, let's generate the random number from the uniform distribution, and second, transform the PDF or PMF to CDF, and then find the value x such that minimizing the fx less than x equal to mu u, okay. All right, so and then once let's say you have this PMF, and then you have a CDF of this PMF, right, like this. So probability value when x equals to -2 is 0.1, right, 0.1, and then it becomes 5, it becomes 6 because we have probability value of 0.5 when x equals to 0. That's why, right? That's why CDF of this function has this shape, and then when x equals 3, there is an additional probability of 0.4, so you can add a 0.4 to the 0.6 at this time. So at the end, you have a value of 1, right, as a CDF, value of the CDF, yes. So once you have this CDF, you can get the random variate from your random number. So in order to get the random number, and then so if you populate, if you look at this chart, this bar, having a value between 0 and 1, then you can see the probability to get the random number, right? So with this probability, you can get x minus 2, right, minus 2, and then within this range, you can get 0, and within this range, you can get 3, right? If you have any value of the mu following the uniform distribution, right, between 0 and 1, and then so you randomly you can get the value, right, within this range, right, because random number following the uniform distribution, right, within this range. And then let's say you got the value of the random number at here, and then based on this, you can determine the value of your random variate, right, which is x equals to 3, right? Got it? So if you draw the arrow and then project this value onto this CDF, and then you will know that okay, your x value is 3, right? If your random number is here, and then your x value, random variate will be 0, and if your u value is in this range or here, right, then your x value will be -2. Good. Okay, so let's look at the overview of the random number generation in simulation. So here is a real machine center, and then we observe the data set, right? We observe the service time of this machining center, right? So here is the part numbers, and then we have service times, right? And then based on based on the observations, you can drive a statistical distribution like this. And then in the simulation model, you can use this distribution, right, in this process. And then by doing the random sampling, or by generating the mu value, you will need to generate the mu value first, which is the random number, and then project that random number onto the CDF of this distribution, right? And then so that you can get the value of the random variate. So x, we can know that in this case, x value equals 3. All right. So desired property of random number generation. We have to obtain different random numbers in different run, right? Because it is following the uniform distribution. So which means all the value within that range in the uniform distribution has the same probability, right? To get each value. So if you make multiple trials or replication, definitely you need to obtain different numbers, right? Theoretically. Also, the random number generation should be reproducible. If a CD, when CD is the same, the sequence of random number will be the same. That's why when you make a multiple replication in Arena, each replication has a different seed. That's why each random numbers are different. Also, it should be fair way. You should have fair way to sample the random number from uniform distribution. And well-known approach is the linear congruential method, also known as LCM. Okay, this is the most common random number generator, and we will learn about this. Okay, let's look at the linear congruential method. So we have recursive formula of the LCM. So here we have Zi, and then capital Zi minus 1. So actually generate the number from the previous Z value, okay? And then A is alpha is a multiplier, A is a multiplier, C is an increment, and M is a modulus. Okay, this is an integer. So Z value is always between 0 and n minus 1. And also you need to define the mu n as shown below. So mu I is equal to Zi over n. So once you have this integer value, you can utilize this Zi value to get the value ui. Okay, and ui value is always between 0 and 1. Got it? So this meets our objective, right? So random number is always between 0 and 1. So that's why. And we are using this certain formula to generate the ui value. So this one also meets this one is reproducible, right? So when you come up with your own formula, random number generation formula, you need to think about seed, multiplier, increment, and modulus. Okay. All right. So let's say the modulus is 63, and then multiplier is 22, increment is 4, and Z0 is 19. From this, actually we can make this formula, right? According to linear congruential method, we can develop this formula, right? And then based on this, we can generate the value of Z, right? So start from you can put the 19 over here so that you can get the value of Z1, right? So if you put 19 over here, you can get the 422, right? And then divide this value by 63, right? Because this is a multiplier, that's why. A modulus, that's why. And then remainder will be 44, right? Got it? Same thing. So put the 44 here so that you can get 972 and divide this value by 63, and then remainder will be 27. And also you can do the same thing. Put the 27 here so that you can get the 598 as a result of this part, and then divide this value by what? 63, so that your remainder will be 31, right? Once you have Zi values, and then you can divide these values by what? 63. right? Because always this value should be less than or equal to less than 63, right? So we get anyway, you can get the UI according to this equation. So these are the random numbers generated by this formula. Okay, and then when I equals to 63, the procedure will repeat. Okay, you can get 19 as a value of zi when I equal to 63, which is exactly same as zi value when I go to 0. So it has a cycle. Okay, and here's the definition of cycle. So period, the length of cycle, the cycle is 63, right? So period is always less than equal to m, and then generator is called full period if p equals to m, 63. Okay, in this case, so it has a full period. The cycle has a full period. All right, let's solve this practice problem, and you can manually generate 3 consecutive random variate following this uniform distribution. Okay, so it doesn't have to be uniform. You can consider the exponential distribution and other distribution. Anyway, see the value is 3. And zi is like this. And now we can actually calculate the zi value. So let's say c is 3, so which means c0 is 3, right? And then plug this value into this equation formula so that you can get the 9 as a value of this, and then divide this value by 5, right? 5, which is multiplier, modulus, and then remainder will be 4, right? 9 divided by 5 give you 4, right? And also, if you put 4 here, 2 times 4 plus 3 will give you 11, and divide this 11 by 5, and then so that the remainder will be 1. Once again, if you put the 1 here, 2 times 1 plus 3 will be 5, and 5 divided by 5 can be divided by 5, so that the remainder will be 0. Got it? And then the cycle will repeat, right? Will be repeated. So in this case, m value equal to 5, and then p value is 4, because we have the length of period is 4. 1, 2, 3, 4, right? So that's why. So we don't have full period. And once you have these 3 consecutive random numbers, which is 0.8, 0.2, 0, right? Consecutive random numbers, right? According to the problem, you need to generate consecutive random variate, right? So we have consecutive random numbers first, and then based on these 3 numbers, random numbers, you can project new one onto the CDF of the CDF of what? This uniform distribution, right? So that you can get the first value of the random variate, and then for the based on the U1 and U2, U3, you can get the 3 different values, random variate, right? And in order to get the random variate, you can utilize this kind of the equation. So if you calculate it, x1 will be 5.6. So this value will be 5.6, and this value will be 4.4, and this value will be 4. Okay? Yes. All right. And linear congruential method, LCM parameters used by Arena until version 3.0 is like this. Yeah, currently I don't know what kind of actually the parameters they use, but m value was a 31st power of 2 minus 1, and a value was 16,807, and C equal to 0 and Z0 was like this. Okay, there are multiple random C. So the cycle length is n-1, which is 2.1 billion. Okay, so that's why whenever you make a random, whenever you generate random values, and then the arena actually can give you the really reliable random values, and then reliable, statistically reliable result. Okay, thank you.